Hello, and welcome to AI for Mechanical Engineering. In the previous lecture, we've learned about multi-channel 2D convolution. In today's channel, we'll be learning some important concepts in convolutional neural networks, padding, and stride. So starting with the first component, strides. These strides determine the increment step size for the convolution operator. In other words, we're simply determining by how many pixels we're skipping at a time, we're moving at a time, both horizontally and vertically. And in this example shown over here, we have a kernel size of 3 by 3 and a stride of 2, meaning that we're skipping 2 or moving 2 pixels at a time. And just like we've learned in our previous lectures, the result or the output of this convolution operator has a size that is smaller than that of the original input. So this, depending on how we select the strides, we reduce the size of the output map. Now the question is, what if we want to preserve the size of the output map? Here we can introduce a technique called padding. And padding simply refers to artificially filling the borders of the image, as shown in this example over here. And the reason why we do this is because we want to keep the spatial dimension constant across different filters. So in other words, we want the shape of our output, or the results of the convolution operation, to be identical to that of the original input. And the way we do this is by adding these additional pixels around the borders. Now, these borders are typically filled with zeros, and we call this zero padding. So taking a closer look at the relationship between padding and stride, let's consider this example over here, where we have an input with the following shape, 5 by 5 by C, and a padding of 1 by 1, and a stride of 2 by 2. And each of these numbers of both the padding and stride correspond to the value of padding and stride with respect to the horizontal and vertical axes. So because we have an equal number of padding for both the horizontal and vertical axes, you would have an equal border that is padded throughout the input image, and also the stride, because it is identical in both axes, it moves 2 steps to the right, or horizontally, and 2 steps vertically. And of course, just like we've done for the deep artificial neural networks, we feed our output values through a nonlinear activation function. So in the fully connected case, we would have each of these nodes, or each of these values, go through some sort of a nonlinear activation functions, such as the sigmoid, hyperbolic tangent, or ReLU. In the 2D convolutional neural network case, you can view this process as feeding each of these pixel values through the nonlinear activation function. Next, I'll be talking about something called pooling. So pooling is a way to reduce spatial resolution, especially for faster computation. And although there are different methods for pooling, for example, if we're computing a maximum value within a given sliding window, in other words, given a certain sub-region of the original image, we're selecting the maximum value. In this case, we're referring to something called max pooling. So let's assume this example shown over here, where we're doing max pooling with a 2 by 2 filter and a stride of 2. We start at this location first, take the maximum value, write it over here, move over 2 steps and find the maximum value, in which we find 8 to be our maximum value. Move downwards and find the maximum value. And for the final subregion, we find 4 to be our maximum value. So this is the result of our max pooling, and this effectively reduces the size or the spatial resolution of the original input. Now again, although there are multiple types of pooling methods, the most standard type of pooling is known as max pooling. So the example shown in the previous slides, which simply computes the maximum values over non-overlapping blocks. So let's take this 1D signal, for example, and we're using a window with a size of 2, meaning that we're looking at 2 pixels or 2 values at a time. So starting with the first 2 values, the maximum of these 2 values is 3. meaning that our outputs of the pooling operation for the first pixel would be 3. Shift over 2 pixels or 2 steps and find that the maximum is 3. And for these 2 pixels, the maximum is 0, 2, and 2. So this is our output shown over here. And you can see that we've effectively reduced the spatial resolution of the original input. So the key takeaway here is that through pooling, we're essentially grouping several activations at a time into a single, more meaningful representation. And again, another example of pooling is average pooling, in which we take the average instead of simply computing the maximum value of the given window. So let's take a look at why pooling provides invariance to any permutation inside a given unit cell. So for example, let's say we have this cell over here and this cell or these subregions throughout the original signal. If we apply max pooling, we end up with the maximum value over here, 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 and here. And the output looks like the following. So what this means is when we look at a slightly perturbed version of this original input, let's say for instance this signal over here, the result of the max pooling is actually identical to that of the previous version. So in turn, this provides a pseudo invariance to these deformations that result into local translations. So just like we've done in the 2D multi-channel convolution case, let's take a look at this step by step. Assuming that we have an input with the following shape, this time, instead of doing a multi-channel convolution, for pooling, we're doing this channel-wise. So meaning that we start off with the first channel, and the result of the pooling operation is shown here. And similar to the way convolution works, we move over depending on what the stride is, except this time we don't have any overlap. And once we move over to our second location, the output is shown over here. And once we reach the end of a row of a given image or a channel, we move over to the next channel. So the next pooling results will be shown over here. And we repeat this process until we reach the end of the first row of all 3 channels. So the next step would be shown in here, here, and then finally here. And once we reach the end of the row for all 3 channels, we move downwards just like we did for the 2D convolution case. So this time we move over here, and the output is shown in the corresponding location. And we repeat this process up until we reach the end of the image. So for all 3 channels, especially in this example, we repeat this process up until we are able to obtain our final output. And our output will have the following shape, where R and S are determined by the size of the pooling window. And one difference, or one thing to note here, is that unlike the 2D convolution, the multi-channel 2D convolution case, this time, because we're doing a channel-wise operation, the number of channels is actually preserved. So if we combine these 2 concepts, first the filtering part and the activation, followed by the pooling operation, we can construct something known as a convolutional block. Now these convolution blocks are known to be the building blocks for typical CNNs, but within each block you have your filter and your activation maps, your feature maps, and once they go through some sort of a nonlinear activation function, we have our activation maps, and once we have these activation maps, we effectively want to reduce the spatial resolution through this pooling operation. So to summarize, we have our input to a given layer. This could be the input layer of the CNN or any hidden layer in between. And the filters extract certain features and go through some nonlinear activation function and reduce the size of that feature map. And you proceed on to the next layer. So this process is repeated depending on how many layers you have for the CNN. So for a typical or the classic convolutional neural network architecture, we first have our input of the neural network, followed by convolutional blocks that I've just described in the previous slide. And within each block, we typically have consecutive convolution operations. So you have your first convolution operation followed by your second. And although the design or the architecture may differ depending on who's designing it, we finally have our max pooling operation at the end of the convolutional block. And because we're assuming that we're solving a classification problem, the outputs, for the outputs, we'll have a fully connected layer for the classifier, and finally a softmax activation to let us know the probabilities of an image belonging in each class. So let's look at an example of how we can use this convolutional neural network or CNN architecture for classification. So in a typical CNN, the first part of the neural network can be seen as learning the appropriate features for that classification task. So we refer to this as feature learning. And we're basically learning to design the kernels or filters from data. And within each convolutional block, we have these nonlinear activation functions, which essentially introduce these nonlinearities through the activation function. And finally, because we're doing max pooling, we can essentially reduce the dimensionality of these images or outputs. And once we have the appropriate feature maps for a given input image, we have the fully connected neural network for our classifier, and finally the softmax, which is essentially a method to tell us what the probabilities of an image belonging in each class. And just like we've done for the artificial neural network case, we train these CNNs using backpropagation. So in other words, we're learning the weights for both the convolutional filters and fully connected layers through backpropagation. And the loss function that is used in this case is the cross-entropy loss. So based on this formulation, let's take a look at how we can actually implement CNN using TensorFlow. So starting off with the architecture of the neural network, or the CNN, we'll be revisiting the MNIST example, which was essentially a data set of handwritten digits. And our goal is to classify which class a given image belongs to. Here we'll be having one convolution operation followed by a pooling operation, and then we repeat this the second time. And here will be our fully connected part, which acts as our classifier. So in order to define the architecture in TensorFlow, we use the sequential API just like we did for the ANN case. But this time, we'll be using a slightly different function here, where we use tf.keras.layers.conv2d. And here we can determine what the number of input filters are, determine what the number of filters we'll be using, which essentially dictates the dimension of the output channel, and our kernel size, the type of activation function that we're using, and what type of padding that we'll be using, and what the input shape is. And for the max pooling, all we have to do is use tf.keras.layers maxpool2d and repeat this process so that we can finish the first part of the CNN. And then for the rest of the neural network or the CNN, we simply have a fully connected neural network, which is what we've seen in the previous lectures. And once the architecture of the CNN is determined, we next have to define what the loss and optimizer is. So this is very similar to the process that was used in the training of simple or fully connected neural networks. But the only difference is that because we're doing a classification problem, we're using cross-entropy as our loss function. And for the optimizer, we'll be using atom optimizer. And finally, for the metrics, we can use accuracy as a metric to assess the performance of our model. And finally, we can use model.fit to actually train our model. And if we train our model, we can evaluate the model using model.evaluate. And this will tell us what the accuracy or the performance of the model is depending on what our metric was. So here in this example, you can see that the accuracy is 98%, which is actually pretty high. And if you want to visualize the results, let's say this is the original input image, and this is our output vector. And again, because I've mentioned that we're using a softmax activation for the final layer, you can see that this vector is a representation of the probabilities of that image belonging in each class. And as you can see in this example, you can see that with great or high probability, the CNN thinks that this given image is or belongs to the class of 9, which is actually correct. Now, if we want to extend this example to the realm of mechanical engineering, let's consider a case where we want to detect defects within this steel surface. So in this example, instead of classifying different handwritten digits, the goal here is to determine what type of defect is within the steel surface image. So here we have 6 different defect types, and you can see that all of these images look slightly different, but for each class, you'll see similar patterns. So the goal here is to be able to train a neural network or a CNN that is capable of classifying these steel surface defect images. Now for the implementation, we'll be using a mostly identical CNN architecture, except this time because we're using a slightly different dataset. You'll notice that the input shape is defined slightly differently, and the corresponding inputs will be slightly different because you're starting off with a slightly different input size. So the syntax for the training will be identical, and for the results, because we only have 6 classes, this time we'll have a vector with only 6 dimensions. And again, just like we've seen in the MNIST case, you can see that with great probability, the neural network or the CNN thinks that this image belongs to the defect of a rolled-in scale. And based on the ground truth, we can say that the CNN was actually correct. So in today's lecture, we finally looked at how we can implement a CNN, what a CNN was, and looked at a couple examples of how CNNs can be used to classify different images. This is the end of today's lecture, and thank you.